Welcome to our lesson on testing claims about proportions. Basically, we're going to learn how to do a hypothesis test around a proportion, so we're dealing with proportional data. Before, we have looked at the basics of hypotheses, and we've seen how we can do both the p-value method and the traditional method, and we briefly talked about the confidence interval method. It's not a really good method to use. So we're really going to highlight mostly the p-value method. You can also use the traditional method or what's called the critical value method. But I strongly recommend you get used to using the p-value method. It really is the most widely used and the easiest one to interpret properly. Alright, there are two different ways that you can test claims about proportions. One, you can use the normal distribution to approximate the binomial distribution, or two, you can use the exact method, which is just based on the binomial probability distribution. We're going to start off showing how to use the normal distribution to approximate it, only because it ties in nicely with how we do tests about the mean. You know, we use a normal distribution for the mean if we know the standard deviation, so it'll tie those two together. But for the most part, if you have technology that will allow you to do so, you should try to use the binomial probability distribution instead and use the exact method, because as statisticians we're always striving for precise answers rather than approximate answers, right? We don't want to approximate unless we have to. Some of the basics when we're dealing with proportions, some of the vocabulary that we've seen before, right? N is still our sample size, p hat is still our sample proportion, which is just number of successes over sample size, right? So X is number of successes. P is the population proportion, and then Q is always 1 minus P. Just like all the other tests, we always have requirements that have to be met in order for these tests to be valid. The first is that we have to have a simple random sample. That's always going to be the case. We need to have the conditions of a binomial distribution satisfied, and if you don't remember what those are, go back and review your notes. We also have to have the additional condition that n times p and n times q both have to be greater than or equal to 5. So whatever your p is, right, then your q is 1 minus that. Your sample size n just has to be large enough so that when you take n times p and n times q, you get a number bigger than 5 or bigger than or equal to 5 for both of those. Just like before, the binomial distribution can be approximated by the normal distribution with mu equals np and the standard deviation equaling the square root of npq. And remember here that p is the assumed proportion, not the sample proportion. Right? It's the thing we're testing against rather than the data that we have in front of us. So it's kind of the assumed proportion that we think happens in the population. Here's the test statistic. Always good to see it and understand it, although we're going to let technology do the heavy lifting for us. But just some things to remind ourselves of, that this is very similar to the z-score that we've seen before of x minus mu all over sigma, right? X being the thing that we have, mu being the thing that it's measured against, right? So in this case we have p hat, we have a proportion of our sample, we're measuring it against the hypothesized proportion from the population, and then we divide by a standard deviation. Well, this is just the calculation for the standard deviation when we're dealing with proportions. So the formatting, the overall form of our z-score is still the same. Again, we have our two different methods, the p-value method and the critical value method. You can use tables or technology for either. Of course, we're always going to strive for using technology. It's easier and it's more accurate, and we're also always going to strive for the p-value method because, again, it's the more accurate and more widely used method. Most of your computer programs, calculators, technology will always provide you with a p-value, so that's one of the reasons why we're going to use it. If technology is not available, you can always use the tables. The critical value method is the same method that we talked about before. The idea is you have your distribution, right? You calculate some cutoffs, and those are your critical values, right? So these are the z-scores in this case that will cut off, you know, whatever it is. If alpha is equal to 0.05 and you're doing a two-tailed test, then you want 2.5% in each tail, right? You want 95% in the middle. So you go and find the critical values that cut those off, right? That give you those cutoffs. And it ends up, if my memory serves me correctly, being 1.96 and negative 1.96. So those are your critical values, and then when you go and get your test statistic, you just compare to those and see, well, did it land on the inside or did it land out here in the rejection regions? And if it's out here in the rejection regions, either above or below, then that's when we know to reject the null hypothesis. So that's the critical value method that we've seen before. The confidence interval method is discussed in some textbooks, so I'll discuss it here briefly just so you know what they're talking about, but it's a horrible method because it just lends itself to a lot of problems. So in general, only for two-tailed hypotheses tests, so right there it's already limited because we can only use it for two-tailed tests. So whenever you do a one-tailed test, you can't use it. So that means it's crappy right there. You can construct a confidence interval around your best point estimates. So you're constructing a confidence interval around your p hat, and then you're just looking to see whether or not the hypothesized p is within that confidence interval. It's got a lot of major issues, a lot of major problems. Don't do it, right? Unless you're in some book or course that requires you to do it, it's not a good method. And here's where they're talking about the problems with that, right? When you're testing claims about the population proportion, the traditional method and the p method both will give you the same result, always, because they use the same standard deviation that is based on the claimed proportion p, right? As we said in the previous slides, we're using the p, the q, and the n that are based on the claimed proportion of the population. However, when you build a confidence interval, it uses an estimated standard deviation that's based upon the sample proportion p hat, and those two numbers can be different, so therefore you can get a confidence interval that really isn't accurate around the claimed proportion p. So it's possible to get a result from the p-value method and the critical value method that is different than the confidence interval method. And what I mean by that is you could do the p-value method or the confidence interval method, the p-value method or the critical value method, and they both tell you to reject the null hypothesis. However, you could then go and do the confidence interval method and it would tell you to fail to reject, right? So that's what we mean by different conclusion. So it's really a good strategy to only use the confidence interval to do your estimation of the population proportion, as we did in previous lessons. So leave the confidence interval to what it's really intended to be, and that is a confidence interval, an estimation of a measurement from the population, right? You build a confidence interval around p hat, you build a confidence interval around x bar, whatever it happens to be. That's really what it's supposed to be used for, and instead use the p-value or the traditional method, which is also sometimes called the critical value method, for testing a claim about the proportion. And I still think the p-value is the best of those two. So my suggestion is go for the p-value. Okay, here's a simple example. So based on some information from the National Cybersecurity Alliance, 93% of computer owners believe they have antivirus programs installed on their computers. We go out and take a simple random sample of 400 scanned computers, and it's found that 380 of them, or 95%, actually do have that antivirus software installed. If we use the sample data from the scanned computers to test the claim that 93% of computers have antivirus software, what is our conclusion going to be? So our first thing to do is check our requirements, right? The 400 computers are randomly selected, so that's good. There's a fixed number of independent trials with two categories. Either they had the software or they didn't, so it meets the requirements of a binomial distribution. And we check NP and NQ really quick and see that because N was 400 and our P, right, was 93. Now remember, the P is the assumed, right, the null P. So our P is this 93% that we're testing, not the 95 that we got from our sample. Right? See, we're using 93. That's the assumed null P, not the P hat. You'll notice there aren't little hats on P and Q in those formulas. So we get 372 and 28. Those are both bigger than 5. So we're good to go. All the requirements are handled. So we can move on to our first step, which is to create our hypotheses, to write our hypotheses. And again, you'll notice that they're not p-hats because we're not hypothesizing about what happened in our sample. We're hypothesizing about what happens in the population. The claim is, right, the original claim is that 93% of computers have antivirus software. So that's the null. The null is that the proportion in the population is actually equal to 93. However, the opposite of the claim is that there isn't 93, right? There was nothing that said, let's test if there's more than 93 or less than 93. It just claimed that there was 93. So the other part of the argument is that there isn't 93%, right? So we're looking for any result other than 93%, which you might think would be really easy to find. And so, how are we going to ever fail to reject, right? You would think that everything would be different than 93, so we'd always be rejecting. But stats is looking for something that's statistically different from 93. So you'll see for the significance level, we're going to let alpha be 0.05. Remember, it's always up to you to decide what your alpha is. Obviously, when you're doing homework and things like that, the book tells you what to use alpha for. But when you're out in the real world and you're actually doing these things for real, you as the researcher get to set your alpha level. And because we're testing a claim about a population proportion, we know that we're going to be using the normal distribution approximation, p hat. And then later we're going to see how we can do this same thing with the binomial. Using the p-value method, right? The next thing to do is to calculate our test statistic. So we have our nice simple formula. We plug everything in. The p-hat is the sample proportion, so that's the 380 out of 400. We're comparing it against the p that we think, the 93% from the population, calculating our standard deviation, everything. Gives us a nice simple z-score of 1.75. Now we can look that up in a table or use technology. But in either case, we end up getting 0.0582. That's the area to the right of our test statistic. But because this is a two-tailed test, we also have to take into account the likelihood of getting something over here, right, that is equally deviant from 93, right, the same distance or farther away. And so we have another tail over here with the same area, so we just double that and get the actual p-value of 0.1164. Well, because the p-value we got is bigger than our alpha level of 0.05, we have to fail to reject the null hypothesis. Then the last step is always the crucial one, where we write this in English. We fail to reject the claim that 93% of computers have antivirus software. So we're concluding that there is not sufficient evidence from our sample to warrant a rejection of the claim that 93% of computers have antivirus software. Even though our sample was 95%, it's not far enough away from 93 to warrant a rejection of that claim. Okay, if we were going to do this with the critical value method, steps 1 through 5 are all the same. Step 6, we still get our test statistic, right? So we still use that same formula or technology to get our z, our test statistic of 1.57. But now instead of getting an alpha level, we're just comparing it to our critical values, our cutoffs. And because it's a two-tailed test, right, and we want to be alpha to be 0.05, we're putting half of the alpha in each tail, right, so 2.5% in each tail, and that gives us a cutoff critical z-score of 1.96. Because our z-score was 1.57, it lands within the white region. It doesn't land out here in the rejection region. So again, we get the same result. We fail to reject, right? And conversely, or I shouldn't say conversely, and identically, the same results before, we have pretty much the same write-up, right, that we put in English, that there's not enough evidence to warrant rejection of the null hypothesis. Now, if we were going to do the confidence interval method, I'm just going to show you this once because I really think this is a horrible method to use, and we can only use it here because it's a two-tailed test. We build a confidence interval around our p-hat. Well, in this case, we get a confidence interval of 92.9, right, so almost 93%, up to 97.1. That's a confidence interval around your p-hat. Now all you do is ask yourself, does P land inside that interval? And because 93% is in fact in that interval, we don't have sufficient evidence to warrant rejection of the claim. So in this case, we do get the same answer, but that won't always be the case, and it's just not a good technique to use. How about using technology to do this? Well, steps 1 through 5 are exactly the same. Whether you're using technology or formulas, you're still going to go through steps 1 through 5. And in fact, whether you're doing the p-value method or the critical value method, you're still going to do the same steps 1 through 5. So now you decide to use technology to get your p-values or your critical values. I'm going to go with p-value just because it's the method I like best. So in our calculator, stat, over to test because we're running hypothesis tests. We have proportional data, and we only have one of them, so it's a one proportional z-test. Your p0, that's the thing that you're testing against, in this case 0.93. Your x, those are your successes, right? We had 380 of them out of 400. And we're doing a two-tailed test. We're just testing for a difference, right? We're not doing a less than or greater than. So then we calculate that. You'll see that it gives us the exact same z-score if we rounded to 3 decimals, right? Or sorry, 2 decimals, we get the same thing. It gives us our p-hat of 0.95, and then this p here, that's not the proportion p of the population, that's your actual p-value, and you'll see that that also matches this to 4 decimal places. It already doubles it for you, right? Because that's what it was figuring out when it was asking you if it was a not equal to versus a less than or greater than. It was then doing the proper calculations for making it a one-tailed versus a two-tailed test. And in this case, it's a two-tailed. What if we want to do it with StatCrunch? Equally simple. Stat, again, we're dealing with proportions. We have one sample. We don't have the raw data. We only have the summarized results. So we do with summary. Number of successes, again, 380. Number of observations, 400. Down here, we just have to change our P, right? This is the P that we're testing against of 93%. It automatically changes this for us. Here is where we would change it to a one-tailed test, but we're doing a two-tailed, so we're going to leave it right there. Tell it to compute, and there we have it. Same results, right? 1169, and our test statistic of 1.57 if we round. So technology just as easy. Okay, what if we want to be accurate and we want to actually do the exact method rather than this normal approximation? Well, we can get exact results if we use the binomial probability distributions. Now in the past, these were a pain in the butt because they're not easy to calculate manually, but since technology is caught up to our needs and it's at a point where it will do all this stuff for us, the idea of approximating using the normal curve has kind of become an archaic practice, and we really don't do it a lot in normal statistical work. It's just used here as a teaching tool. The other nice thing about using the binomial probability distribution instead of the normal is we no longer require NP and NQ to be greater than or equal to 5. So we can use this method whenever we have a really small sample that doesn't get us NP and NQ greater than or equal to 5. So that's also kind of nice. To test the hypothesis using the exact binomial distribution, all we have to do is just run technology on a binomial instead of on a normal. And again, you're going to want to use the p-value method here. It's just better. If you're doing a left-tailed test, then the p-value is just the probability of getting X or fewer successes among n trials. Because if you draw a picture, as I tell you guys all the time, draw a picture. Now I know the binomial curve doesn't look like this, but you just give yourself a curve for reference. If we're doing a left-tailed test, then we're looking for things down here. Well, that means we're looking for things below a certain point. So that's why we're looking for the probability of getting X or fewer things amongst our n trials. Because remember, the binomial just becomes bars, right? Instead of a curve, we just have a bunch of bars. And then if we're doing a right-tailed test, of course, we're looking for X or more things. A two-tailed test, well, if the p-hat that we have is greater than the p that we're testing it against, then our p-value is twice the probability of getting X or more, because since it's bigger, we're doing to the extreme, so that or more. And then if the p-hat we have is less than the p that we're comparing it against, then we're looking for x or fewer things, and then we double it. Okay, so it's pretty intuitive. It makes sense that if our hypothesis is something bigger than what we're seeing out of our sample, then we're looking for the probability of getting something that small or smaller and then doubling it. And if our sample ends up being bigger than our hypothesized p, then we're looking for something that extreme or bigger, so we're looking for x or more successes. Here's a simple example. We're going to test the gender selection method, that X sort thing we've talked about. 10 randomly selected couples are treated with that method. 9 of the babies come out as girls. We're going to use an alpha of 0.05 to test the claim that with this method, the probability of a baby being a girl is greater than 0.75. So we're testing against 0.75, not 0.5, even though we know in the real world, with no intervention, the probability of having a girl is just 50-50, 0.5. Step 1, just like before, we write our hypotheses. So our null hypothesis is that the world works, like we assume it to be, with the p of 0.75, and then the alternative is what we're trying to prove here, that if we use this method, p is going to increase, right, and be bigger than 0.75. So we're now doing a one-tailed test, and in fact, in this case, we're doing a right-tailed test. So our p-value is going to be the probability of 9 or more successes among 10 trials. Now, why is it 9 or more? It's 9 or more because 9 is what we got from our sample, right? So it's more because we're doing a greater than, and it's 9 or more because 9 is what we got from our sample. Next, we throw it into technology and we get these probabilities, right? So here's one example of technology spitting out binomial probabilities. So here is the probability of exactly 9 and exactly 10, and then over here they give us 9 or more, right? 10 or more, and the 9 or more is what we're looking for, the 0.244, which is what we got here. The probability of 9 or more successes is 0.244, or if you saw before, it's just the probability of 9 plus the probability of 10. So that becomes the p-value of our hypothesis test, which is a pretty big p-value, and it's a lot bigger than 5%. So we fail to reject the null hypothesis, which means there isn't sufficient evidence to support the claim that with this method the probability of a girl is greater than 0.75. Now obviously it would always be better to be precise rather than do approximations. So the question arises, when do you use the exact method? I've already discussed this. We're going to try and use the exact method whenever we can, whenever we have technology that allows us to do the exact method. That's what we should do. If we don't have technology that will allow us to do the exact method, then we can do the approximation. But technology is so good that it can do these things for us all the time. Just to show you how easy it is for technology to do these exact ones, here's our calculators, right? You can go back to your distributions menu because we're dealing with the binomial distribution, and you're going to want to use the cumulative function, right? And that, remember, adds up probabilities of a binomial from 0 up to a certain point. You have to give it npx, where n is the number of trials, so 10, comma, 0.75, that's the probability of a success, and then comma, you give it what you're adding up to. And since we want to know the probability of 9 and above, we want to add up from 0 to 8. And then what we're looking for is 1 minus that. So I'm going to do minus 1, and then of course my answer is just not negative. 0.244, you can see it's the exact same number down there from our output. You can also do the binomial PDF and then store your results in a list and get this exact same list that you get out of StatDisk. Okay, so that's how to do it in the calculator, very easy. How about StatCrunch? Even easier. Stat calculators, right? Whenever we're dealing with distributions, we want to go to our calculators, and we have a binomial distribution. Tell it our n, which in this case is 10. The p is 0.75. We're looking for the probability that x is greater than something, and in this case greater than or equal to 9, and there's the exact same 0.244, blah 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 blah. Okay, very easy to do with technology. Technology is the way to go here, and always, when you can, use the exact method. That's it.